Using our inverse function rule, we're going to add another function now to our library of standard functions, and that's the natural logarithm. So y equals ln of x. Now, the natural logarithm is the inverse of the exponential. So y is the natural logarithm of x precisely when x is e to the y. So we'll call this function g and this function f. Really here we're interested in f dash and not g dash. So we should really write this the other way around, shouldn't we? So f dash of x is 1 over g dash of y. Now, if x is e to the y, then g dash of y is again e to the y. This is the magical property that the exponential function has. So the magical property that e to the y has. When we differentiate it with respect to y, we simply get the same function again. So 1 over g dash y is again 1 over e to the y. But we want f dash of x, so we want everything in terms of x. But luckily x is just e to the y. So we can substitute that in and we find 1 over x. And this gives us the important rule that if y is the natural logarithm of x, then dy by dx is 1 over x. And there's another function for our standard library. It's going to turn out that differentiating the inverse trigonometric functions is going to be very useful. Surprisingly useful, in fact. Later on, we're going to meet something called integration, which is kind of an opposite of differentiation. So in fact, it turns out that, while the inverse functions themselves are not so interesting in themselves, that they do occur rather often as evaluations of integrals. So let's start by thinking a little bit about the inverse functions. So here I've drawn the graphs of sine and cos, which is just a shifted version of sine, of course, and tan. Now all of these suffer from exactly the same problems that we had earlier for y equals x squared, that there's no unique answer for any value of y. So if I choose, say, y equals a half, here there are infinitely many values along here for x, such that f of x equals a half. We only want one value if we're going to define the inverse function. So in fact what we're going to do, exactly as for y equals x squared, we're going to miss out half of, or we're going to miss out in fact almost all of the possible x values, and we're simply going to take all the x values here between minus pi over 2 and plus pi over 2. So this is pi over 2 and minus pi over 2. And so what we get is that if x lies between minus pi over 2 and plus pi over 2, then y equals sine of x if exactly when x is sine inverse of y. We can do exactly the same for cosine, but that range there doesn't work. That's that range there. If we have a half, then there's still two values. Instead, we're going to choose 0 up to pi. So in the region from 0 up to pi, we can say something exactly the same for the cosine. So if 0 less than or equal to x less than pi, then y equals the cosine of x precisely when x is cos inverse of y. And for the tangent, we can use exactly the same region as for sine, namely minus pi over 2 up to plus pi over 2. So again, in this region here, if I give you any one value of y, there's a unique value of x that gives that value of y. So we have exactly the same as we did in the top formula. So y equals tan of x here if and only if x is tan inverse of y. Next, we're going to use the inverse function rule to differentiate the inverse trig functions, sine inverse, cos inverse, and tan inverse. Well, actually, I'm going to do sine inverse and tan inverse, and you're going to do cos inverse as an exercise. The inverse trig functions in themselves are not all that interesting, but what we're going to see is that when we differentiate them, we get some rather simple functions. Later on, we're going to meet integration, which is a kind of opposite of differentiation, and the fact that the differentials of the inverse trig functions are so simple means that they arise quite often as values of integrals. Let's start with sine inverse of x. So we put y equals sine inverse of x, and this is what we'll call f of x. And y equals sine inverse of x precisely when x equals sine y, and that's only valid between pi over 2 and between minus pi over 2 and plus pi over 2. So I've exchanged the x and y from just a moment ago. So sine of y is gy. We're interested in working out what f dash of x is. So here's the inverse function rule. F dash of x is 1 over g dash of y. Just rearranging the formula there. So this is 1 over, and then g dash of y is just cos y. Now x is sine y, and we've got cos y here. We'd really like to write this in terms of x, so we have to rearrange it a bit. So how are sine y and cos y related? Well, we know that sine squared y plus cos squared y equals 1. So cos squared y is 1 minus sine squared y, or 1 minus x squared, and so cos y is the square root of 1 minus x squared. Now actually we should really be slightly careful here. We don't really know whether this is the plus square root or the minus square root, but by drawing the graphs, in fact, you can see that f dash is always increasing. So in fact, the gradient must always be going upwards, and the gradient must always be positive. So that tells us we should be having the positive square root here. So here's another standard differential. If f of x equals sine inverse of x, then f dash of x equals 1 over the square root of 1 minus x squared. Your turn now. In exactly the same way as we've just worked out the derivative of sine inverse of x, show that if f of x is the inverse cosine function, then f dash of x is minus 1 over the square root of 1 minus x squared. And let's do the last of the inverse trig functions, y equals tan inverse of x. Of course, y equals tan inverse of x precisely when x is tan y, and of course we again have y lying between minus pi over 2 and plus pi over 2. So here again we can write f of x for tan inverse of x, and then the inverse function is g of y. And we're interested in finding out f dash of x, which we can do using our formula here. F dash of x equals 1 over g dash of y. Now g of y is tan y, and when we differentiate that, we're going to get sec squared of y. And again, we want to write this really in terms of x. So x is tan y. So we have to ask ourselves how tan y and sec y are related. We can use our formula here again. We just divide everything in the formula here by cos squared. Let's write it in terms of y, because that's what we're going to be using. So sine squared y plus cos squared y equals 1. And we just divide everything by cos squared y. So with sine squared y over cos squared y is tan squared y. Cos squared y divided by cos squared y, well, that's obviously 1. And 1 over cos squared y is sec squared y. So sec squared is 1 plus tan squared. That's great, because tan y is x, and we're interested in sec squared. So this is just 1 over 1 plus tan squared y, which is 1 over 1 plus x squared. So now we've differentiated our we differentiated our last inverse trig function. So if y equals tan inverse of x, then dy by dx equals 1 over 1 plus x squared. And that's another nice differential we're going to add to our standard library. So here's a summary of all the inverse trigonometric differentials. Exercise. So in exactly the same way as we just differentiated the inverse trig functions, we can also differentiate the inverse hyperbolic functions. So as an exercise, use the relations cos squared minus sine squared equals 1, which we then divide through by cos squared to get 1 minus hyperbolic tan squared equals sec squared, and show that if y is the inverse hyperbolic sine of x, sine inverse of x, then dy by dx is 1 over the square root of x squared plus 1. If y equals cos inverse of x, then dy by dx is minus 1 over root x squared minus 1. And if y is tan inverse of x, the inverse hyperbolic tangent, then dy by dx is 1 over 1 minus x squared.